Hello everyone, we're Group 55. Today we'll be introducing searchable symmetric encryption, for short SSE. The presentation agenda will be as follows. The first part will be the introduction, which will mainly focus on the background and the components inside SSE. The second part will be SSE main, which will focus on the algorithm behind SSE. The third part is application, which we will introduce the real application of SSE in industry. The last part is analysis, where we will discuss the pros and cons of SSE, as well as the future direction of SSE. With the development of cloud computing, encrypted data stored on database have become more common. That arises the issue on how to search encrypted data fast and secure without sharing important information to server. SSE provides a solution to this issue. SSE is a type of algorithm that allows users to search documents by keyword while the documents are encrypted. This is implemented through a trapdoor function that allows searching. A searchable encryption scheme includes data owner, semi-trusted server, and users that are allowed to search. There are four components in SSE. A key generation algorithm run by the data owner that generates secret key K. A security parameter K is used as input. Secondly, a keyword index generation algorithm run by the data owner. It takes the secret key K and a set of documents D as inputs, and outputs a keyword index I. Thirdly, a keyword trapdoor generation algorithm run by the users. It takes the secret key K and the query keyword W as inputs, and outputs the trapdoor TW for the keyword W. Finally, a keyword search algorithm run by the server. It takes the keyword index I and the trapdoor TW as inputs, and outputs a set of document DW that contains query keyword W.
Now let's look at an example, which is the first SSE scheme proposed by Song's team. Firstly, Alice, the user, wants to store a document in the database. The document contains a keyword W which is n bits long. Now she encrypts this W with the function here, using a secret key to get X. After this, she split this encrypted X into two parts, L and R. The length of L is n minus m, and the length of R is m. Then Alice generates S, which is also n minus m bits long, and a new key using the function here, and also with the previous secret key. After this, she can use a function capital F with the S she generated to get F new key S, which is m bits long. Now she can combine S with F new key S, which is in total n bits long, and do an XOR operation to the combination of L and R, which is X, the encrypted keyword, and pass the result C as the keyword along with the document to the server. Whenever Alice wants this document, she can send a combination of X, which is encrypted keyword, and the new key to the server, so that the server can try to find the document with the keyword C, which XOR X, and gets n minus m bits long S on the left and m bits long F new key S on the right. This is because one thing XOR another thing twice is still the same, so that S and F new key S XORed with L and R, which is X, before pass it to the server. Now the server XOR it again with X, so the original S and F new key S should appear. Therefore, Alice can find her document. Now let's move on to the static SSE versus dynamic SSE. The normal static SSE contains three elements: setup, token, and search. The token here is for searching for the document. This means you cannot modify the document collection on the server. If you want to insert or delete a document in the collection, a dynamic SSE scheme is required. There are 7 elements inside dynamic SSE, which are setup, token, search, same as a static SSE, plus insert token, delete, and delete token. As if you want to insert a document, you also need a new token to find it. In deletion, it's the same. You also need to delete a token while deleting the document. Now, we have introduced the single keyword search. However, if the keyword does not match the one stored, you cannot find the result. This will be extremely inconvenient in the real life, isn't it? People make typo all the times. Therefore, fuzzy search is important as it can tolerate minor typos and formatting inconsistencies. For example, this team, introduced a fuzzy search collection using added distance to measure keyword similarities. There are multiple ways to measure the added distance. The one they use is the number of operations to change one word to another. The operation includes substitution, deletion, and insertion. When the user is searching for something, if the exact matching failed, the server will collect the keyword within a predefined distance and return the collected set. Besides fuzzy search, conjunctive keyword search is also practical. A user can acquire a document containing several keywords with the use of conjunctive keyword search. Compared to the single keyword search, it is more effective and appropriate for practical application. Google's team proposed the first two conjunctive keyword search schemes. They are based on the model that generates a capability to help the server determine whether a document contains a given keyword or not.
Now we're gonna talk about the real-world application called the curable encryption from MongoDB. This feature was released on July 2022 and is still under development. The reason for supporting this feature is to deal with a critical situation where the database is fully compromised or the client wants to protect the sensitive data. How does it work? In the initial setup, before the documents are sent to the server, the document will be encrypted with the standard AEAD encryption, and all the sensitive fields are encrypted with a 256-bit SSE key, and then they are stored in the safe content area. And all the operations are performed on the client side, so the security is guaranteed. After the setup, when the client sends an encrypted query, the MongoDB driver will generate a search token with SSE key stored at the key management system. Then the token is sent to the database and use SSE to compare the field. Finally, the matching document will be sent back. From the figure, we can see that the search token and the encrypted field are totally randomized. So it's hard for the attacker to leak any useful information. The system above is great on protecting confidentiality, but there are some limitations. Firstly, the query only supports for equality check instead of keyword searching, which make it less flexible. Secondly, use of the above system costs more memory than the normal database setup.
Now we'll discuss the pros and cons of SSE. The advantage of SSE is that it provides a solution that enables users to search encrypted documents on a database in linear time. On the other hand, the disadvantage is also very obvious. For example, the application field is limited to cloud computing, while other platforms could store plain text in the database and encrypt the communication channel in between, which is a more convenient way.
For the future direction, although SSE is powerful, there are still some improvements that can be made. Firstly, we can make the SSE perform search on multiple kinds of documentation, like image or videos. And secondly, we still need to improve the efficiency of the algorithm. Like currently, most of the SSE runs in linear time, but if it runs in sublinear time, I believe it can be more popular. Yeah, that's all of it. Thanks.